So we're just gonna get started. First off, I want to go over what actually is machine learning. We hear that a lot, and it's kind of used in a lot of buzzwords. Like with tech articles, they just love to throw machine learning at anything just to make it seem like a little bit more popular, a little bit more techy. But really, machine learning is nothing more than just an algorithm that learns through historical data. So we're trying to emulate what a human brain does and kind of learn through experience and learn through seeing things over and over again. And that is what we're trying to create with code. So the actual foundation of this requires lots of statistics and math knowledge. However, due to Python being the best and R and MATLAB or whatever programming language you want to use, there are a lot of fundamental packages that you can use in order to kind of avoid those crazy statistics and math and just get to coding instead. So with machine learning, you can really do whatever you want. You can predict future data. You can do like time series forecasting. So for instance, with like stock prices or like real estate prices, you could do object classification. So can a piece of software differentiate between a cat and a dog, etc. It can really do anything that theoretically a human can do. And it can be implemented in many different facets. So we can do classification. So like I said before, with the image recognition, we could do regression. So with time series forecasting, and we could do clustering. So kind of grouping pieces of data together in order to get more contextual evidence for a certain thesis that we might have. So how do we actually implement it? In order to do this, we have a lot of different mathematical models that we can use. Some are regression-based, some are tree-based, some are like neural networks. So this is like another big buzzword. This refers to deep learning, where we're kind of creating programmatic nodes of neurons that kind of represent our brain's neurons. And from there, we're able to do like a little bit more complex of machine learning models. And in order to code this, we can use Python and one of the Python's packages, scikit-learn, in order to get started. So scikit-learn is kind of like the base level Python package for machine learning. It does a lot of great things, and it is kind of like the foundation of machine learning. So if you recall from our previous BDAA workshops where we're talking about pandas, pandas is kind of like the underlying infrastructure for like data science and data manipulation. It's kind of the same thing here. Scikit-learn is kind of the baseline foundation for machine learning and deep learning. So we have to kind of follow procedures for doing machine learning, and not just machine learning, but for all data science. Obviously, with this being a bait club, we hear a lot of business analytics and like artificial intelligence. And one of the biggest buzzwords that we hear is data science and what that really is. But it is kind of like universally well known that data science is kind of like a 6-step procedure. The first one being problem definition, which we kind of do by figuring out like, hey, what questions do we want to have answered? And you'll see that that kind of mimics the final project that we've assigned by Jay in the first slide that we had. The second will be data preparation. So kind of using your pandas and your NumPy skills to like clean your data. Then we have data exploration. So using your analytical skills to figure out contextually what our data is really saying, what is within the data that we can kind of extract to kind of gain more useful information. Then we have modeling. So this is the actual machine learning aspect where we're finally creating a classifier or a regressor or whatever you want, fitting it towards our data so that it can do some machine learning task. After that, we do evaluation. So answering the question, hey, is this model worth our time? Is this a good model? Would I have better success choosing a different model and things like that? And the last step, which we aren't going to be going over today, which would be deployment. So how can I actually use my model in real time to solve problems in real time? But like I said before, universally, this is kind of the 6-step process for data science. And we're going to be covering, well, I guess we'll be covering the first 5. So the fun part of this is how do we actually code it? I like to break this down into like really like small, I guess, micro steps. This is kind of the approach that a lot of people would recommend that you do in terms of actually implementing machine learning into your projects. The first thing is obviously you need data in order to do anything. So the first thing would be to fetch your data. Next, before we do anything else, we want to make sure that we're doing contextual things to it. So cleaning it up, making sure that there's no quote unquote holes in it, and doing like data exploration as seen in the previous slide. Then we're going to choose our models. And this is kind of where knowledge of statistics and math is kind of necessary. But for right now, we can just kind of ignore it just because it is a workshop and I don't want to be showing you a lot of theory. But choosing models is very, I would say, like background theory heavy. So that's something that we would have to consult like Google for, I guess. Next is splitting the data into a train and test data. So this idea of train test split is kind of a really fundamental idea. And we'll go over that a little bit later. But essentially, we want to have the ability for our models to train on a specific data set so that it can actually learn the patterns and the tendencies that the data has. And then with the remaining pieces of our data that weren't used in training, we want to use that for testing purposes. So the reason why we don't want to train with 100% of our data is because data is kind of a finite resource. We only have so much data at our hands. So if we use all of it for training purposes, we have no more data to test it. Because if we were to test using data that we use to train the model, obviously it would be able to understand those recognitions because the model learned through that particular piece of data. So that is what you would call overfitting, but we will get to that in a second. So the 5th is actually training the models on test data. And 6th is then predicting the values of that test data using that model that has already been fitted. Next, we're going to evaluate the model performance. So the way that I like to do this is I evaluate model performance altogether. So I train and test multiple different models and then evaluate them all at once and choose the best one. And the next step and the final step would be to optimize your best model or models. So out of all of the models that had the best percent of chance getting something right, right from the get-go, we're going to take that model and fine tune it a little bit to make it even better. So now with that, we're going to jump into actually coding it. I'm just going to stop sharing my screen for just a second so that I can get to Jupyter Notebook. So if you don't already know what Jupyter Notebook is, I'm sure if you've been following BDAA, you already do. But just for those who do not, it is a tool for you to write Python code in like small little cells so that you can execute like little tidbits of code without having to run the entire script top down. So let me just pull this up. Okay, can everyone see my Jupyter lab?
Yeah, we can see it.
Awesome. Okay. So the first thing that we're going to need to do, so I'm just going to go straight from the slides. The first thing that we need is to load our data set. So we're actually going to be using, if you guys recall, in a previous workshop, I used what is called the iris data set. So it is a data set with like information on different like iris flowers. And it's a very popular data set that we use because it's kind of like introductory. It's very clean. It kind of makes a lot of this stuff that you might be seeing for the first time very easy to understand. So in order to load this in, first we're going to get the URL for it, and then we can read it in through the URL. So I'm just going to paste this right here. So we are going to read this this data set using pandas or PD, but obviously I don't have that installed yet. So I'm going to import pandas as PD. And I'm just going to read CSV with the URL here. So if I run this right now and I kind of do like a df.head to see all the data, you'll see that it's kind of like messed up right here. The reason for that is because the actual data frame doesn't contain like the contextual information. So like, what do these numbers mean? So in order to remove that error, I'm just going to add in a few contextual details for this data set. So the first number is going to be the sepal length. Next is going to be the width. And then same thing for following ones are going to be petal length and petal width. And then the last one is going to be the classification of this flower. So now I'm going to pass in the names equals names. And if I do this, you'll now see that our data is working properly. So for our 0th entry, we have a sepal length of 5.1, sepal width of 3.5, et cetera, and this is an iris setosa. So just for contextual sake, I get, or context sake, these are in centimeters, but that's not really that important. Anyway, the next step is going to be exploring or cleaning our data. So the first thing that we want to do, and you may remember this from our data manipulation workshop, is are there any holes in our data sets? So I'm just going to label everything just so it's as neat as possible. There you go. So in order to check this, we can do like a is null on our data frame. So our data frame is called df, which is our iris data set. So we can just run df.isNull, and if we look through, everything seems to be false, but there is a lot of information that we're missing. So I'm just going to instead run df.isNull, grab the values, and see if there are any NaNs. So this would be the syntax for seeing if there's any NaNs, and you'll see that it outputs false. And that is because like all of these aggregated together mean false. So that's good. That means that there are no holes. The next thing that we're going to do is we're going to explore the data. For the data. Okay, so there are some things that we might want. The first thing would be, what is the shape? I guess like some like statistics on each metric, and like the size of each of the classifications, I guess. So like how many of each classification are there? Does anybody remember how to get the shape of a data frame? You could type it in the chat and just like drop it if you have a guess. This was something that we've gone over for, I believe, our data manipulation or pandas workshop. But it is a built-in method. And if anyone has it, yeah, perfect. df.shape. That gives us all of the information that we need for how many rows and how many columns we have. Good job. So I'm going to just do a print statement again, just so it's a little bit more neat. Data set shape, and then just run df.shape. So if I print this, it says 150 and 5. So this means that there are 150 entries and there are 5 different features. And that obviously makes sense because we have sepal length, width, and class, which is 5. Perfect. So now we have the statistics on each metric. So this would be things like mean, standard deviation, statistical quantiles, things like that. So in order to do that, we're just going to print df.describe. And if I hit print, it'll show a bunch of different statistics. So count, mean, standard deviation, mean, max, and like I said before, the quantiles. And the last thing we want to ask is how many of each classification are there? Well, that's pretty easy to do. We can just print the size of the data frame if I were to group it by the class. So I could do df.group by class. So I'm just going to print this first, and we're going to see that it is just a regular pandas core, which is like, done by a group by. And if I wanted to show the size of each of them, then I could just do this, and it'll show us that each of the flower types, I guess, have 50 entries each. So that's good to know. It's very well evenly split. And the next thing that I want to do is kind of like look at the distribution of everything for each metric. So this is kind of valuable just for receiving context. Again, this entire like EDA or exploratory data analysis is kind of trying to gain context for this information. There was a question, can you also use value counts? Yeah, you definitely can. You just have to input it 3 different times. So if you need to say, I'm just going to type in right here. Also, yeah, there you go. If I just type in here like df.iloc where class, or sorry, df at class equals iris setosa, and then dot size even, whoops, dot size. No. Oh, wait, it's not a dot size, sorry. It would be a len. So this, wait, location. Okay, I messed something up here, but essentially, I don't know why the syntax is slipping out of my mind, but you are correct. Like you could use like value counts, and you can also use like the length of an iloc. So like that's also good to know. But I just find that like this is kind of the fastest way to do it, just because it already groups it up by classification. So anyway, going back to looking at the distribution and the relation for each metric, there's a really useful tool that is already built into pandas. So I'm just going to import plotting from pandas, and inside of here we have something called scatter matrix. And I honestly really like this just because it looks like it gives you a lot of information just from like a single line of code. So we could just run a scatter matrix on DF. And what this does is it generates an n by n plot where n is equal to the number of features that you have. Obviously, it's quite small, so I could just make that bigger by saying fig size equals, I don't know, I'll do like 15 by 15. So now you'll see that we have kind of like distributions here. We have like scatter plots here, which kind of like give you kind of an idea of what the distributions are. I'm actually going to zoom out a little bit so you can see the entire thing at once. So underneath here is like sepal length. So the distribution charts are corresponding to like these like XY coordinates right here. So this is sepal length, and you'll see like this is like an abnormal kind of distribution. Sepal width seems a little bit more normal. Petal length, not as normal, and neither is petal width. And we kind of see with like these scatter plots. So for petal width versus petal length, we kind of see like positive correlative like values. So we can kind of like see that, there's like an obvious linear distribution here. But yeah, like we're just kind of trying to get contextual like data for what these metrics are doing for each other. So I find that this scatter matrix is really, really helpful. So I guess that's enough for EDA. We can now start choosing models. So for the purposes of this workshop, I'm just going to choose a few models that are like kind of different just for variety's sake. So some things that I'm going to take are going to be a, I guess, tree classifier. We can do a regressor. I guess like a naive Bayes model and non-parametric, I guess. So I'm just going to explain this a little bit. I did say before that I don't want to get into like high theory, but essentially these four are quite a few different mathematical models that we use in machine learning. So the first one is going to be a tree classifier. If you've ever taken, I guess, data structures, you may have learned something called a tree. So like a binary tree where you're constantly asking it like yes or no questions. And if it's yes, you like proceed to the right node. And if it's no, then you proceed to the left node. But essentially, if you do know what I'm talking about, that's kind of how tree classifiers work. So in regression models, we're kind of doing something different where we're building a linear model, using like y equals mx plus b, but with obviously multiple different metrics. And we're kind of trying to build like linear correlation between multiple different metrics and the y value. And our y value in this case is actually going to be a classification. So naive Bayes is built upon a really big like probability discussion, I guess. It's this whole naive Bayesian theory of probability. And the last one, non-parametric. Non-parametric is actually like an umbrella term, which means the model does not need to know any assumptions about the data. It could just start working right from the get-go. So cool, we got over the boring theory. Now, for the tree classifier, I'm going to choose something called a random forest classifier. Again, this doesn't need to be that big of a deal. I'm just like choosing random ones. This one, I guess, is a logistic regression. This is, there's only really one option, which is Gaussian naive Bayes. And non-parametric, I'll just choose like KNN. KNN means K nearest neighbors. Again, another like high theoretic stuff. But I chose my models. So now the next step is actually going to be to like code them out. So everything here belongs to a library. So everything that I just mentioned here is supported by sklearn, and we could import all of these. So I can import the linear model is for logistic regression. So I'm just going to do this. Ensemble contains a random forest classifier. Neighbors is obviously going to be KNN, which is K nearest neighbors. And the last one is going to be the naive Bayes. Okay, cool. So now we have these imported. Now, neighbors, I think. Did I spell this wrong? Import K neighbors classifier. Hold on. There you go. It was a capital N. Okay, so now it is a really simple way of creating these classifying objects. The only thing that we have to do, so I'm just going to create the random forest classifier first. We're going to call it RFC, and we're going to set equal to just an object, random forest classifier. And that's all I need for a model. Like we just completely avoided like grad school and just essentially made a model in like 5 seconds. And obviously it's not that easy, but it kind of is. We essentially imported a bunch of different mathematical tools in order to create a model. And now we can readily use that model for any sort of classification that we want. So I'm going to go over the next ones. We're going to have a regressor. This one actually contains a few parameters that you don't need to worry about, but these are essentially added because of the fact that our data set is multi-class, meaning like we have multiple classes. So like if you look back here on our data sets, obviously like there's multiple classes here. And liblinear is just going to be saying that we're using a linear model. Now we're going to create our k-nearest neighbors classifier, and then our naive base. Okay, so I understand that was a little bit painful. It seemed like I was just pulling a bunch of code from like what seemed to be like the ether. But really, it's really simple. A lot of this you could see in like the front page of documentation for like scikit-learn. So now what we can do is split our data into training and testing data. So if you recall, I stated something about train test split. Now, in order for us to do that, we actually can just avoid having to like do that manually and use a scikit-learn package. So this is called model selection, and we can import train test split. So now I'm just gonna like give you guys a quick quiz. Train test split requires the X values and the Y values. So I'm going to like reprint out our data frame. Does anyone know how to split up our data frame into our X columns and our Y columns? So in other words, what I'm asking is there a way that I can extract specific columns from our data frame? So if you have the answer, you can like type it in the chat. Okay, it does not seem that, oh yeah, one person, so DF at sepal length. So that is a really great point that I would like to bring up, is if I were to just do this, it actually gives me just the one column. And now that's really close, and I like that you brought that up. But do you know by any chance how to grab multiple ones? So I want like a way to get like sepal length plus like this, like sepal width. And this doesn't actually work, but like conceptually, that's kind of what I want.
You just add a comma after sepal length and then put the column.
So like this, or we could try that.
You need the brackets. Like
yeah, there you go. Perfect. Well done. So in order for you to do this, you actually have to pass in a list. And in here, you're passing a list of all of the column names. So if I do that, you're actually getting sepal length and sepal width. Awesome, good job. So I'm just gonna pass in the rest of them. So petal length and petal width. And this is gonna be our X. So let's just say X equals. And then obviously for our Y equals, we're just going to do class. So let's just print out our X to see that that's working. Yep, 150 rows by 4 columns. That seems about right. And there's 150 different classifications. So cool, we've successfully done that. Now the reason this is important, like I said, is because train test split requires an X and a Y. So let's just do this. Now, in order for us to use train test split, this actually gives us, this returns a X train, X test, Y train, and a Y test. So I'm going to explain this in just a sec, but first I'm going to just type it out. So let me just comment this out and say this equals train test split, and I'll pass it my X and I'll pass it my Y. Now there are two other things that or actually really just one other thing that I need to pass in, and that is going to be the size of my test data set. So this is going to be test size equals. Now, what this means is just try to understand that train test split is literally, like I said in the PowerPoint, splitting our data up into data that we want to train our model on, and then data that we want to test our model on. So how big do we want our test data set to be? Normally, we want to do like somewhere near an 80-20 split. So our test size is going to be 20% of our entire data set. So I'm gonna make it 0.2. And the last thing I'm gonna put in is just a random state. You don't have to do this, but it's just for anyone else who's going to be following this. If you want to get numbers that are exactly the same as mine, you can just copy this line like random state so that everything that has been randomized is going to be like pseudo random, where it's going to be the same random values that I get. So I'll just leave that for anyone. Okay, so like I said before, here our training is going to be 80% of the data set. And just copy this up here. Cool. So now we have our X train, X test, Y train, and Y test. Now the next thing to do, the exciting part, is train or fit our models on test data. Now it's literally as simple as, so let's just use our logistic regression, which is regress. It's as simple as doing regress.fit and then passing in our train data. And now it's fitted. So now all we have to do is test or predict our models on test data. So in order to do this, you would do something like regress.predict on X test and Y test. You would just do this. You would just do this, and it would send you an array of all of the predicted values that it would give. However, this doesn't really tell me much. It's just telling me a bunch of like predicted values. So what I could do instead is I could just do regress.score and pass it in the X test and the Y test. So what this does is it runs a regress.predict on the X test and then gives you back a score of the predicted values versus the actual values. So in order to kind of make this neater, I'm going to create a print statement for it. So score is this. Cool. And if I run it, you will see that I created a model that is 100% accurate. So this is what you would call overfitting, which is what I mentioned in the PowerPoints previously. This model is essentially stating that I have 100% accuracy on this model, which is a score of 1. But it's obvious that this is not the actual case in the real world. So how can we get a real representation for like the accuracy of this model? Because obviously it's not going to be 100% accurate. No model is going to be 100% accurate. In order to avoid overfitting, we can use a method called k-fold cross-validation. So I'm going to write this out. K-fold cross-validation, avoid overfitting data. So essentially, this method is a way to test our model by splitting our data multiple different ways. So when we use train test split, we split our data into 80% train and then 20% test, only one time. But if we use k-fold, so for instance, if we use like 5-fold, we can split our data 5 different times and get our score for the model 5 different times with 5 different data set splits. So we're training our model and testing our model with 5 different combinations of our data set. And then we evaluate the mean of those 5 different scores. So essentially, if I split our data up one way and then another way, and then do that 5 times, I can then get a more accurate representation for how good our model is while not overfitting, because it's trained on like so many different like sequences of data. So yeah, I hope that makes sense. But yeah, from here on, we'll just use a k-fold cross-validation to get a more realistic model score. So I'm going to show you how to do that. In order to do it, it's literally just you first create a k-fold object. So actually first we have to import our k-fold, which is again in model selection. So we're going to import a stratified k-fold. Let's see if that works first. Awesome. And then we would do like a k-fold object. So how many k's? We could just say like number of splits is equal to k. Let's just say like 10. And we would have to shuffle this to make sure that we are like actually randomly generating and getting a different combination of all these data sets. And for anyone who is following along later or now, I'm just going to set the random state to 1. Then I would do a cross-validation score. So I would have to get the score of all of the means for each different iteration, like I said before. And this is also a built-in method. So this is also model selection. And we're going to use cross-val score. Now, I just want to like mention this again. Like notice how we're using a lot of pre-built methods. And that's kind of like the beauty of like modern programming with data science is we can kind of just get away with not knowing that much theory. Obviously, it's going to be kind of important in the real world, but just for like learning's sake, it's pretty helpful. So right now I'm just creating a cross-validation scoring metric. So I'm passing in like a model, like some like random model. This isn't defined yet, but we're also going to pass in like our train data, our different cross-validation. So this is going to be our k-fold object, which is right here. And we're obviously scoring on accuracy. So that's essentially how you do it. So now I'm going to train this, I'm going to like test this on a bunch of our different models that were defined up here. So in order to do this, I'm actually going to create a list of models. And I'm going to append all of these models into this list so that I could like do it simultaneously, if that makes sense. So I'm just going to create this list. So this one is the regressor or linear regression. This one is going to be our random forest classifier. This one is going to be our k-nearest neighbors. And this one is going to be our naive phase. And which one was this called? NB. Okay. So now I have a list of models. And this is just an example code. So like, don't mind this. I'll actually just comment all this out. So like I said before, for each model in this list of models, we're going to run k-fold and then get our cross-validation score. That is not how I thought it would format. There you go. Okay, so let's import like last time. We're just importing this. So now we're actually just going to like do this piece of code right here, but for every model inside of our list. So obviously, in order to iterate through them, we'll just do like 4 xn models. But x is actually going to be a tuple. And inside of that tuple will be the name of that model as well as the model itself. So instead, I'm just going to avoid that problem and just say for name model. So this actually like decouples it. So now we have the name of the model as well as the model itself. So all we do is just copy this line of code that I previously wrote. So now we have k-fold and the number of splits, like I said, is 10. That's fine. Shuffle's true. That's cool. And then we're going to create our cross-validation results. So instead of passing in model, we're going to, oh wait, actually, yeah, we'll just pass in model, which is this right here. And And then the last thing we're gonna do is we're going to print the actual results. So if this syntax doesn't make sense to you, do not worry about it. So what was that? Okay. So I'm going to pass in the name and then the mean results as well as the standard deviation for the results. So CV results.mean, like I said before in the theory for cross validation, we're just getting the mean of all of the different splits, and then we're also getting the standard deviation. So, for name, comma, results. What am I missing here? Oh, that's a from. It should be for. There you go. So now we see that we're finally generating some metrics. So our logistic regression is 95% accurate. Our random forest classifier is 93% accurate. Our KNN is 94% accurate, and our naive Bayes model is 94% accurate as well. So now is our time to evaluate model performance. So obviously, our logistic regression has the best accuracy, and this is 95%. So we're going to use logistic regression to optimize our best model. So we didn't really talk about what optimizing our best model really means, but essentially, we know now that our logistic regression model is our best baseline performer. So we can choose that model to be the one that we want to optimize. And what optimization actually means is we want to do something called hyperparameter tuning. So hyperparameter tuning. Essentially, this is like the methodology of finding a model's hyperparameters and changing them until it gives us the best possible accuracy. So these hyperparameters aren't something that can actually be learned by the model. They're given externally. So we are going to, be the ones that are giving the model that. So there are two main methods. So just two main methods for hyperparam tuning. There is grid search, and there's going to be also random search. We're just going to focus on grid search. So grid search takes a huge list of different values for hyperparameters and then literally just brute forces through them. So if you think of kind of like a two-dimensional array, so pretend that these are all hyperparameters, 4, 5, 6. What grid search will do is literally match them up for every single different combination that you can think of, and then it'll test it. So let's implement that. Let's implement that first and see how it does. So in order to do this, we import grid search, which again is from sklearn's model selection. And now here is the point where I'm actually going to figure out what the actual hyperparameters are for our model. So like I said before, logistic regression is our model that we want to optimize. So I'm actually going to I'm going to stop sharing really quick and just share the entire screen. But here is the documentation for scikit-learn. We have some parameters, the first one being penalty. So this is just like a normalization method. Again, don't have to worry about the theory. And another one is like the C value. So these are two parameters that we can actually use in order to do hyperparameter tuning. So let's implement that really quick. Okay, going back to, here you go. Cool. You guys can see the Jupyter Lab, right? Okay, so let's implement this. So for penalty, there were values L1 and L2. And for C values, it was defaulted at 1, but we could try 0.5, 1.0, 1.5. 2.0, 2.5, and 3.0. And then let's just make this into a dictionary. So C equals C and penalty equals penalty. If this doesn't make sense to you, we're essentially just creating a dictionary. So I'm going to print out, I'm just going to print out the hyperparameters. And you'll see that it's literally just a dictionary. So now with this dictionary, I'm going to actually create a grid search. So let's like fit these models in with our parameters once we find them. So let's just create another model for logistic regression. Like the same way that we did it before. So this was a syntax. And now we're going to actually create a grid search model. So let's just call it LR. And here we're using grid search in order to find the most optimal hyperparameters inside of this object. So we're passing it in our model, our hyperparameters, and the amount of like cross validations that we want. I usually stick with 5, but it's really up to you and like how strong your PC is. And now from here, we're going to extract the best model. So we'll just do an lr.fit on our trained data. So once we get that, we can actually find the best penalty, as well as best C value. And in here, we're going to print out best model dot best underscore estimator underscore. Now this is all in documentation, but I kind of have it memorized, as this is something that you will oftentimes do, especially when you're doing hyperparameter tuning. So best underscore estimator underscore dot gets params, and in here we want the C value. So once we print this, you'll see that we actually have our best penalty of L2 and a best C value of 0.5. So this is essentially now telling us, just to explain this code a little bit more, is that from our grid search, we have found our best hyperparameters after we fitted it into our actual data. So this right here is the best possible method, our best possible model, given the different hyperparameters that we've given it. And we trained it on the data set for X-train and Y-train. And then we were able to extract each of the best model parameters using this line right here and this line right here, these last 2 lines. So these are our best hyperparameters. Now we finally optimized our parameters, and that's really it for grid search. If you're curious about random search, we essentially do like literally the exact same thing, but instead of going through all parameters, we randomly select the hyperparameters. So this just like reduces compute time while still performing kind of well. But anyway, let's finally test it. So I know that I've kind of like gone over a lot of things, but if you recall, the first thing we want to do is get our k-fold object. So remember, we're still using cross-validation. So the number of splits, like we said before, is going to be state, or it's going to be 10. Our random state is going to be 1, and we still want to shuffle it. And now we have our optimized model. So let's create our optimized model by creating a logistic regression model with the values that we have found using grid search. So we have a C of 0.5, we have a penalty of L2, and our solver, this is things that we've had like prior. So cool, now we have our actual optimized values. So in order to get the results, we just do CV results. And instead of typing this all in, I can just go back up here and just grab it. So we're using cross-val score, but instead of model, we're passing in our optimized model, which is, like I said, our logistic regression. And we're passing it our X-train, our Y-train, our K-fold, and obviously we're scoring it on accuracy. So now we're going to print it just like the same format that we did in our for loop before. But instead of this, percent %s, we're going to type logistic regression optimized, and then remove our name. All right, so for the big finale, we have optimized our model. After selecting a base model, we finally figured out that logistic regression was the best one that we want to choose to optimize. So we only want to pick the best of the best, and from the best of the best, we're going to improve it using hyperparameter tuning. We did hyperparameter tuning using a grid search, and we did a grid search on penalty and our C value. And from there, we got our best hyperparameters of L2 for penalty and a C value of 0.5. So now we created a logistic regression model using those parameters of L2 and 0.5. And now we're going to run a cross-validation schematic and see if it is actually better. So finally, we can run this and we will see that it is at a 0.94% accuracy rate. Now, if we scroll up, we'll see that we actually went from a 95% accuracy rate to a 94% accuracy rate. And in this case, unfortunately, we obviously did not outperform our default model. But that's kind of the world of machine learning. And that's just something that you're going to have to continue to try in, is finding better hyperparameters. But this is something that happens and it's not something to get beat up about. But that is kind of the beauty of machine learning, is you kind of get to be experimental and try different things. But in any case, that's all I have for you guys for the workshop. So thank you so much. Let me just go back to the slides really quick, just for some last minute things. Here we go. So if you were here for the real points, you can scan the code right on the screen. If you have any questions, please feel free to either hit them up on the BITS Discord or email at bits.rutgers@gmail.com. Please follow us on all of our socials at Rutgers_bits. And yeah, that's it. Thank you guys so much for coming.
I got a question for you. Not exactly about the presentation, but I'm kind of new to Python, and I was wondering if you had like any resources or anything that you would recommend to learn.
Yeah, for sure. So I think that if you are new to Python, the first things that you want to kind of have a strong like fundamental understanding of are the packages that I mentioned before that we've kind of gone over in the previous BDAA workshops. So NumPy, Pandas, and some data visualization tools like Matplotlib or Seaborn. Because obviously, like with this workshop, we've kind of seen that everything was based around pandas and like a bunch of different import statements that we're able to use. So I think that once you get comfortable with actually like getting a feel of data and how to manipulate them, the rest comes easy. So in terms of actual resources, you can look on our YouTube page where we have our different workshops. Free Code Camp has a bunch of different articles, as well as medium.com. They have a lot of data science tutorials for intros, like intro to like machine learning or intro to like deep learning, things like that. So if you're more of like a visual learner in terms of like YouTube videos, Free Code Camp is great. But if you want to learn through like articles, medium.com or Data Science Bootcamp, I think it's called. Those are also great articles to look at.
Okay, yeah, thank you.
Yeah, of course. Okay, I'm going to end the meeting here now, if that's fine.
Good job, Dad.
Appreciate it, man.